Okay, let's continue. We start to look into transformation of PSZ, partially stabilized zirconia. Application that you see is in dental. Zirconia. What is zirconia? Zirconia is some oxide, CaO, MgO, and so on. They can produce very high fracture toughness. So these are the three crystal structure. They're monoclinic, trigonal, cubic, and so on. So you're familiar with phase diagram. So here you have MgO. So if you look at this phase diagram again, this is a bi-material phase diagram. So as you go to the far right, you have more MgO, right? So here you have 0 MgO, means you have VZO and so on. Then temperature, then liquid 3000, drop down, you get different phase of the material. So you have monoclinic, trigonal, and so on. All this you can directly read from the phase diagram. Okay. Again, you should be familiar with what is the few names on the few diagram. For example, we call eutectoid, eutectic, all these things, right? So you drop from liquid. So the first point on here, this is the point of the last drop of liquid that you see, right? Then you start to see solid solution plus liquid. So here also you have a pro-eutectic and so on. Right? Then you drop and then you see other things. Okay. So there's a question why you cannot fabricate articles from a pure zirconia. It's because pure zirconia from tetragonal to monoclinic structure, they are martensitic. So of course this name is a bit deep for you guys, but this is a name for material science. They cannot be done by rapid cooling. Okay, you cannot see this one by normal rapid cooling. Okay. Okay, so you can add in another type of oxide to extract the zirconia. So you add like 10% of CaO, MgO, and so on. So like on this phase diagram, you see MgO and zirconia oxide, like VO, to stabilize the zirconia. The rest you can read from the phase diagram. So here, partially stabilized zirconia contain 9% mole of MgO. So here you read the unit on phase diagram. This is not WT percentage. This is mole percentage. So here you will see about 9% is about here. Here. Okay, so here then you read from vertical mixture of 9% of MgO. It happened at about sintering process about 1800 degrees C at this line. Then rapid cool to the room temperature in all metastable circuit structure. So means you start from here, because you want to start from a cubic solid solution, then you cool down to get monoclinic solution. So if you drop down, then you reheat again. You drop down to room temperature, then you reheat up to 1400, and then you maintain a certain time, a fine metastable submicroscopic with the tetragonal structure, you'll see a metastable grow into the grain of the material. Huh? So you see something like this. Huh? Right. So again, I don't ask you this one in the test. Huh? Okay. Yeah, seen this table before, and what are the, if you pull the tensile stress both sides, so you see the crack will go in here. So if you look at zirconia, MgO, the fracture toughness is given here, 8 plus, 7.26, and so on. So zirconia, they are quite good when handling crack. Huh? So their value is higher than others available ceramic material. Next, we look at thermal properties in ceramic. So here, if you increase the temperature, and then the y-axis here is thermal conductivity level. Thermal conductivity. You try to recall your experiment that you use candle, and then you find the time for the pin to drop. So same with this one. As you can see, different material give you different thermal conductivity. So some increase, for example, powdered MgO. If you increase temperature, the thermal conductivity become better and better. But some become worse and worse. For example, pure dense DEO. If you increase temperature, the thermal conductivity will drop. And so on. So again, recall this one, I think it's chapter 1, chapter 2, or even chapter 3 that deal with a defect. So this is an interstitial defect. So this is if we have a positive charge interstitial, then you have a extra positive charge there. Then if you have empty, then you have a Hessian vacancy. You have empty of the negative charge, then you have anion vacancy. Okay, so you have a few types. Either you have more positive charge, less positive charge, or missing one positive charge. Okay, the rest is self-explanatory. So you look at the diagram, you already know already. Okay. Okay, then it come to your test 2 area. Last week I told you, right? This name, right? This name, right? Okay. So when you have a defect, there's a calculation to calculate the concentration of the defect. Okay. So if defect involve Hessian means positive charge. If it link with the positive charge, vacancy. If vacancy charge missing, the name for that defect is called Frankel defect. Okay, so it's formed by a cation leaving its normal position, means missing the positive charge is missing. So there is no change in charges because the cation maintain the same position charge as an interstitial. So it's just leaving the position only. It's still somewhere, it goes somewhere within the site. So there's no changes of charges. Then this one. This one, when there is a number of cation vacancy over cation interstitial defect pairs, then we will use Frankel defects. We have this formula. So important. So Frankel defect, or numbers of defect pairs, or concentration of cation vacancy over Fr equal to N exponential minus Q divided by 2 KT. Okay, again, this formula won't be given. So when you have exponential for E in the calculation, you need to use ln. When you have ln, then you can straight away calculate the value. Okay, this one put to the left. Right? Okay, Q is the energy and number of lattice site. K Boltzmann constant. T is the absolute temperature. Okay. Yeah. Another one is called cation vacancy. Pass is a Skokie defect created by removing. You're removing one cation and one anion from the interior of the structure crystal, then replace them with both at an external surface. You take them from one of the thing, then you put in another side. Okay. Again, important to maintain neutrality in the negativity. So for Skokie defect, you look at the formula. It's the same as the FR equation just now, right? It's just what is different from the previous one is you're looking at temperature, right? Looking at temperature. It's the same structure, Both also calculating cation vacancy, anion vacancy. It's just that when you calculate for Skokie defect, you need to use Skokie defect energy. Yeah? It's just the energy level is different. Okay. Again, what is Skokie? Skokie, you remove one pair of positive and negative charge. Then where you put all these positive, negative at the external surface. You remove it, then you need to use the Q value for Skokie effect. So again, recap what is Franken. Franken is you calculate the insertion defect pass depending on the temperature. Right? So you can see here. Huh? And here Q, again, Q is the energy for Franken defect. Huh? The difference here is the Q value. Okay. The question you will see in test 2 will be specific to one of these. You will mention or use calculate what Skokie defect or Franken defect. Okay. So be careful on the value that you use. Okay, then chemistry definition, stoichiometry. You know, stoichiometry is a balance equation in a chemical. So stoichiometry, when you see the word stoichiometry, it means the exact ratio of positive negative anion in the chemical formula. Means the chemical is balanced. Right? For example, H2O, to make it a stoichiometric equation. Right? Two hydrogen combine with one oxygen become water, stable. Right? So NaCl is a stoichiometrics. So NaCl combine 1:1. H2O is two hydrogen, one oxygen, 2:1. Okay. So again, ceramic, they are non-stoichiometric. Ceramic, they are non-stoichiometric. If there is any deviation of this exact ratio, so when this case can be happen, when non-stoichiometric can happen, when two valence or two ionic states exist for one ionic type. For example, forum, you know, you have forum 3, forum 2, and forum 3. So you have 2 positive and 3 positive. Okay. So as you can see here, if you have a different type of ferrum, then you will form non-stoichiometrics. Right? Because the more electron charge you have, smaller size, right? So 3, 2, and then oxygen. Then these are the how they form the crack, right? How they form the crack. So then is from the presentation of the crack, you know where is the origin for ceramic. So if you see there's a impact, then the crack will propagate from the center of the origin. This one very direct, right? Bending, you will see there's a river, there's a one straight line, and then there's a cabang at the end. So here is the origin. If you try to bend the ceramic material. Then this is a torsion. If you twist, normally in the ceramic, you have a diagonal straight line because of the crystal structure. Okay, if you twist it, then you will have a diagonal. Especially glass. If you try to imagine glass, you try to twist a glass, you also seeing a diagonal shape of crack. Bottle, if you have internal pressure, so it depends. So internal pressure, for example, bottle, you will still see there's a almost diagonal shape also because it's expand outside. This is a schematic of a fracture surface of the brittle ceramic. So if there is it's like glass. Imagine this one as a glass. So if this is a source of failure, then it will propagate outside. So you have a smooth mirror, then you have a mist region. You have a dot, small dot there. Then they have a hacker region. Okay, something like this. Okay, yeah, something like this. So you have a origin, and then mirror. Then you have a mist and hackers. Okay. Okay, example 4. How we apply the formula. Very direct. If you read the question, it asks you to calculate the Schottky defect. So same, you change the Q to Schottky. Right? Schottky defect per cubic meter in potassium chloride. Potassium chloride at 500 degrees C. Energy required to form is given. Density given. So what else? Yeah. Then you apply the formula. So NS equal to N exponential minus. Don't forget about the minus. Minus QS divided by 2 KT. You need to convert all the for example, temperature, you need to convert into Kelvin. All right. So chapter 4, this is chapter 4. You need to calculate the N, right? The N, number of lattice site per cubic meter. So N equal to NA rho divided by AK plus ACL. Right? So Avogadro number 6.0022 10 power 23 atom per mole. Then density, AK is the potassium, atomic weight 39. This one you read from periodic table. You will always see periodic table for this module. Cl is 35.45. This one also from periodic table. Okay. So you put in all the value. N equal to Na 6 point something, 10 power 23, multiply by the 9.5, 1.9. You need to change cm to meter cube. Why meter cube? Question asks you, force you to do in meter cube. If the question didn't mention this, well, you can do in cm cube. Right? But it's always good to practice, calculate everything in unit SI. Okay. So you put in everything, will be meter cube, and then you can cancel the mole over here. Huh? You can cancel the gram, cancel the mole, then you'll get atoms. How many atoms? Huh? So again, remember this formula, huh? How to calculate the number of lattice sites. So you have 1.8 10 power 28 lattice site per meter cube. You have this one, substitute inside there, right? Okay. Then Q is given 2.6 EV, 2K change 500 to, let's say K is a constant value, 8.6 EV per K. We are using K because we are given EV, yeah? Right? 8.62 10 power negative 5 EV over K. Constant, this value, K value is constant. And remember to change 500 degrees C to Kelvin. You substitute, then you get your NS. NS equal to 5 point something, 10 power 19 defect over meter cube. Okay. Just a very direct equation. Only need to memorize the K value, 8 point something. K value won't be given in the assessment. You need to memorize. Number of Avogadro also, we assume you already know, so you won't be given. Atomic weight, you can read from the periodic table. In assessment, we'll give you the formula of that material. For example, potassium chloride, we'll give you KCl, a bracket KCl in the question. Okay, what are the ceramic phase diagram? This, before I forget, this one come out in your final. Okay, you will see this one in your final. And you need to detach the graph from the last page of the question, put in all your answers on the graph. Yeah, so for this module, remember you need to detach one of page of the question paper, then you stapler together with the answer script. Huh? All right, so phase diagram, you're familiar. On the top is percentage or mole, on the below is weight percentage. For metal, you don't see mole. Right? For ceramic, you'll see one more axis over there, and then temperature, and then you read the title of the graph, it will be composition of Cr2O3, means the more you move to the right hand side, you get more this component. So this is a combination of two material, aluminum oxide and chromium oxide. Okay, so when you read this graph, important is that you have liquid, then solid. Inside here is liquid plus solid. Okay. Okay. Then this is another one, also ceramic, the phase diagram. You have composite of weight percentage of aluminum oxide and MgO. Okay, the more you move to the right hand side, you get more aluminum oxide, and then temperature. On the top is mole percentage. So don't mix between the top axis and bottom axis. Right hand side is Fahrenheit. We won't refer to Fahrenheit. Okay, so again, liquid, and then you drop down, you get solid, and so on. Okay. So go and again studies what is eutectoid, pro-eutectoid, and all this. Okay. Okay. So there is a phrase is called spinner. Intermediate phrase is called spinner. They have a formula, AgLO formula. It is here. Spinner is non-stoichiometrics. You know just now what is definition of stoichiometrics? When you have a different, just now we show you the ferrum. Now is on the either Mg or Al. They have a different charges as you decrease the temperature, right? Limit solubility in MgO. So here there's a limit here, it's about 1400. So no more ALO can be dissolved in MgO. The maximum is here, right? So below there's no more you can dissolve. Huh? So 2 eutectic is found on this phase diagram. So again, eutectic is the last drop of liquid that you can see on the graph here. One is here. Okay, so here, so you have these two. Okay, last drop of liquid. So you have here and here. So you have 2010 degree here, about 2000, 2000 degree. Okay. Then this one, another ceramic phase diagram. This is ZRO2 and CaZRO3. Zirconia, calcium phase diagram. Okay. This one is a W percentage below. On the top is mole percentage. Left hand side Celsius, right hand side Fahrenheit. Okay. So liquid always on the top. Then as you drop down temperature, you get solid. It depends on what you have lah. Okay. So in here you have one eutectic reaction where this happen here. Right? It will happen at 2000 degrees C and so on. Okay, the rest you read. So, and then you have a 2 eutectoid reaction which happen at 1000 degrees C and at 850 degrees C. Okay. This is another one, phase diagram. So again, here is SiO and aluminum oxide. The more you move to the right hand side, is more aluminum oxide. Temperature Celsius left, frequency in Fahrenheit on the right, mole percentage on the top. So again, liquid drop, you get solid, right? And so on. So the rest you read. Okay. All this you can extract from the phase diagram. So our first diagram important is that you just extract where is the point length. Okay, just copy whatever you see on the phase diagram. Okay, we start to go into composite already. We have already done ceramic. We done ceramic. Now we go into composite. Now composite is a combination of two or more different material. In this here is combination 2 or more micron constituent that change the properties of the materials. So classification, composite contain one or more phrases. They are considered as a reinforced phrases. There are two, and then another one is if they reinforce, then we call it matrix phrase. For example, fiberglass. So there are different ways of categorizing the composite. Different textbook have different ways of categorizing. But in general, some author they group by type of the ceramic composite you have, the shape of the the alignment of the matrix inside there, the size of the reinforcement, and so on. So why do we use composite? So all this you can read lah. All this you can read. I'll just give you all the mechanical properties. Composite, they are lightweight, low density of matrix. They are strong and stiff reinforcement. So if the original material, they are weak in pulling, you just add in material so that it becomes strong in the tensile direction. So if the material is weak in compact, you just add material so that the compact strength will be better. Okay, so they are strong in stiff reinforcement. The word is keyword is reinforcement. Then you have a high specific modulus or specific strengths. Means the E value will be very high. Because of the amount orientation, so the strength of stiffness also you can control. Two disadvantages, because you add in additional small matrices, right, small particles inside. So you have a low ductility and low impact resistance. So normally composite, they are very weak in impact, means you punch it, then it breaks already. Okay. So there are two formula, specific modulus here. Specific modulus is E divided by rho. Specific is you look at the density, right? For example, this one specific modulus is E. Specific word is you divide by density. Specific strength, what is strength? Strength, you look at a UTS. Ultimate tensile strength was the maximum point of the tensile graph divided by density. Okay, so don't confuse with the normal modulus and specific modulus. Specific means you need to divide by the density. Yeah? Okay, so straight away application. So here you have a Kevlar. Unidirection means same direction, Kevlar. Kevlar 49 fiber epoxy contain of 60% by volume of Kevlar 49 fiber and 40% resin or epoxy resin. Okay, so this composite, you have 60% Kevlar and 40% epoxy or resin. Density, Kevlar is given 1 point something, and epoxy density also given. So when you mix two material together, you need a formula to calculate the properties of that combination. So there is a formula there. So what is the weight percentage of Kevlar and epoxy resin in the composite material? This is weight percentage, WT%. So you are given the percentage volume. Here is given by volume. Density is given. So you need to link volume and density together to get weight percentage. What is the average density of the composite? So again, it's a very basic formula, mathematical formula. So we always start with one assumption. For example, previously we take 100 gram or 1 kilogram of material. Here, because the question give you in volume, so we just assume we have one perfect volume is 1 meter cube. Right? So inside 1 meter cube, inside that 1 meter cube, so we have 0.6 meter cube of Kevlar and 0.4% of epoxy. Then from here, since we have volume already, then we can continue to calculate. Density, you take mass divided by volume. Right? So mass of Kevlar, you pull your volume to the left-hand side. Right? Density equal to mass divided by volume. So how to calculate mass? Mass equal to density multiplied by volume. So you take density is given 1.48 multiply by the volume 0.6, right? You get the mass of the Kevlar in 1 meter cube of assumption, right? 1 meter cube assumption. So inside 1 meter cube, you have megagram, or you can put in kilogram, 888 kilogram also can, right? Why I put in megagram? Because the question give you in megagram. So I want to simplify all my calculation. I don't need to like, of course you can change this one in kilogram if you want, right? So you do the same for epoxy. Epoxy, you take the volume multiplied by the density, you get uh, 0.4. So total mass in 1 meter cube, you get 1.3, about 1.4 megagram. Okay. So I think the important part is that you need to assume how many material you have. In here, this case, you assume 1 meter cube. Then you go for the mass. What is the total mass in 1 meter cube? Okay. Then how to calculate weight percentage in 1 meter cube? So percentage is you take 0.8 Kevlar divided by total mass. Right? This is weight, so you take the total weight. What is the ratio for Kevlar? So 0.8 divided by 1.36 times 100%, you get the percentage in weight percentage. So if you're lazy to calculate for epoxy, you just take 100% minus 64.9. Right? Because total is 100%. Or you can do the calculation also. 48, 0.48 divided by 1.3. Right? You add up, you get 100%. Okay. So for this module, minimum 2 decimal place, maximum 3 decimal place. The answer. Although in the tutorial question or example, sometimes we use full number, sometimes we use singular number, right? Singular decimal. Okay, so here we get the weight percentage already. So how you get the average density? Because this is a combination of two material. So average density, you take rho equal to m divided by v. So the total weight is 1.3, volume is 1. So the density of the combination in 1 cubic meter, 1 meter cube is 1.368 megagram per meter cube. Okay, so this is the answer. Okay, this is the answer for average density. Okay, quite direct lah. Okay, then the rest we look at the properties already. So tensile strength, how many percent? Tensile stress, how many megapascal? So this is the tensile curve. So as you can see, all the name on this graph is the composite. So normal and all these. All right. So how you apply this graph? Normally, either tensile strength is given or tensile stress is given, or modulus E will be given. When you have modulus E, you're able to find either of the numbers here. Okay, the E value of this one. Okay. This is specific tensile. Again, what we mean by the mean specific, you need to divide the parameter with the density. Okay, when you see specific, whether it's modulus, specific modulus means E, the E value divided by density. Okay. So you can see if the specific density increasing, then some of the value will increase also. So it depends lah. It depends what application you want. Okay? Same with specific tensile strength also. Tensile strength is the maximum point of the graph. Maximum point of the graph divided by density. Okay. Okay. Carbon fiber. Carbon fiber is very common nowadays. If you all. So carbon fiber, they have fiber and matrix. Fiber is very good to give you high tensile properties. Fiber is like a rope with a rope inside there, so they are very good in pulling. Matrix, they are carrier of alignment of the fiber and contribute some impact strength. Matrix, you can imagine as a glue. You put in glue and the rope together, you get composite. Okay, so normally matrix we use epoxy resin. So epoxy resin is like when you do the lab test for material under microscope, the round things and the metals inside, the plastic things that surrounding the metal plate, that is matrix. That is matrix. That is epoxy resin. Okay. So how do you form composite? You take fiber plus matrix, you get composite. Okay. So when it comes to assessment, you can either get the name of the composite, you calculate how many percentage of fiber, how many composite, how many percentage of matrix. Okay. So this is again properties of the composite. This is a fatigue properties. Fatigue means there is a dynamics loading, so number of cycle, maximum stress. This one is in imperial unit. So you can see, for example, Kevlar. Kevlar, if you increase the number, it will drop a little bit only, but epoxy and the S glass will drop very significant if you increase the failure. Right? The shape of the graph will tell you the behavior of the materials. Means E glass and epoxy, they are very weak in the number of cycle compared to Kevlar. Okay, then there is arrangement of the material, carbon fiber, epoxy material. So they are laminate. Laminate means by layer cakes like that. So layer by layer. So each layer in material is called lamina. So this is unidirectional and multi-direction. Unidirection means every layer or every lamina, they are same orientation. For example, 0 degree, 0 degree, 0 degree, 0 degree. So they just laminate on each other. Multi-direction, you change the direction. For example, first one is 0 degree. Second one, you turn 90 degree. Third one, you turn 45. Third one, negative 45, and so on. So there is like orientation for that. So this changing of orientation will help to increase the properties of the material. Because sometimes you pull at a certain material, a certain layer will handle that stress. Okay. For example, if you look at the left-hand side, the unilateral, they are not good in bending. If they bend, then this one will break. But here, this one is very hard. This one might break already, but it will handle by other layer. Other layer still holding. Now you start to look at a few equation. Equation for elastic modulus for composite this is also important. All right, this is also important. So here, if you look at layer of matrix, so you have fiber and matrix. In composite, it's important that you know there is a fiber and matrix. So this like a layer cakes or lamina. So in this case, you have a tensile loading. You pull at this one. When you read the question, important to look at the question whether is this way or this way. Different. It's a different calculation already. So then there's an area of composite, length of composite. So this type of loading is called isostrain condition. Isostrain means all the layer have a same deformation. So we'll derive the elastic modulus. We will change our elastic modulus in terms of EFEM, which is you'll see fiber. If you see a small f means fiber, m means matrix. And the volume percentage in VC means the complete one, the composite. VF means the fiber, VM means matrix. So there are only two things in composite, fiber and matrix. Then you combine fiber matrix, you get the composite. Okay. The formula is very basic. If you have a loading, then both fabric fabric fiber and matrix will handle the loading. So the total force applied on the composite will equal to fiber forces and matrix forces. Okay. So again, recall what is stress. Stress equal to force divided by area. You change the forces in stress and area. So force equal to, you pull the A to the left-hand side, you get stress A, right? So you just change force to stress A, but you maintain left-hand side is composite, fiber, matrix. Okay, since the length of layer fiber is equal, so the area can replace by volume fraction. Okay, so you change the area into volume fraction. So A become volume fraction. Since volume fraction of total composite is 1, is VC equal to 1. Volume fraction means VF plus VM equal 1. Equal this one. So if you have an iso strain condition and good bonding, you have a different, you have an equal strain, means deformation is composite will be the same as a fiber with the same of your matrix. We are using strain, equal strain. We use strain formula. Then we put the two equations together. We put the two equations together. You take what again? What is the formula for Hooke's formula? Do you remember? Hooke's equal to stress equal to E and strain. Modulus Young equal to stress divided by strain. So here you look at 1 and 2. If you take 1 divided by 2, you get E value. Right? You get E value. So you divide lah. You divide. Then you'll get EC equal to EF VF plus EM VM. Make sense? This is called rule of mixture for binary composite. Important. Important. Very, very important for your coming test 2 and also final exam. I won't ask you the derivation, but this is the one that you should understand where you get this one. Right? So you should already know what is E definition. Again, Hooke's law. Hooke's law, you write this one and then you elaborate lah. Okay. If you scared, you forget this one, you just try to derive from the top lah. Once you derive from the top, you will see the missing parameter inside the equation, then you can solve the question. Right? Okay. Okay, the rest you read. So if you take the ratio loading, if you want to find the ratio loading, if you want to calculate ratio between fiber and matrix, so you take fiber, we divide by matrix. Force of the fiber divided by matrix. Again, what is force? What is loading? What is stress? Stress is force divided by area. So you take this one, write in the stress and area. So you divide, then what is Hooke's law? This is E strain. This is E strain, and then this one you remain. Then you know that this one is the same. The strain of the fiber and matrix is the same, so cancel. You get this one, EF equal to AF divided by EMEA. So again, since the length of the matrix is the same, you can write A equal to area equal to volume in volume term. Okay, so you have two important formula. One is this one is this one. Sometimes the question gives you the ratio between the fiber and the matrix. So you use this one to calculate what is the missing. Either one of these will be missing. And this one you can find in the table. E fiber, E matrix in the table. So you find out what is the metric used, you substitute value here, and then the area will be given, the length of the matrix and so on, you can calculate. Okay. Okay, I think we stop here. We continue next week. So next week we will apply this equation.